everybody. All right, so here we are continuing on with our lessons on work and energy. Here we are talking about work. Before we start, though, just make sure everyone, please stay safe. Okay, I know these times are weird and things are different. Here I am teaching you guys from my office with the curtain behind here. The curtain. Okay, so things are different. I am aware, and just please, um, as I put onto our Discord, the 3 rules of this time: stay safe, stay home, do physics. Okay, and remember, rules 1 and 2 supersede rule 3. Okay, so if you have time, do some physics, take your mind off things, and we'll talk about work. Let's do some work. Okay, do some work. So what is work from a physical sense? We talk about energy, right? Energy is the idea. We had a whole bunch of energy, different types, and energy is how we do things. Energy is why things happen, right? Uh, there's some sort of potential energy that makes things happen, or things are moving so they have a type of energy, or something like that. The energy makes the universe function, right? And it does things through what we call work. And in this case, what we're talking about here is the physical proportionality between work and position. So if I do some work on something, if I move something, I move it from position x1 to position x2. I've done work. If I've applied a force, if I'm pushing on something, I push something down the hall, I apply a certain force on it, it moves a certain amount. That's what we call work, a physical point of view. This is the physics definition of work, not how much homework you have to do and all this stuff. The physical definition of it. And it can easily be expressed as, here, this is the work is equal to the force times the displacement. Notice these are all scalars. Okay, there are more complicated ways of defining these things in terms of integral calculus and vector calculus and stuff like that, where we talk about these things as vectors. All we're talking about these things purely from a scalar point of view, which is the force, the displacement, and it's in a unit we call joules. Okay, and notice from this is force, that's newtons. This is displacement, so it's meters. So 1 joule, and by necessity, that's not the word, by necessarily has to be 1 newton meter. Okay, and again, we can define newtons as 1 newton meter is 1 kilogram meter per second squared, otherwise known as 1 kilogram. Oh, sorry, this is times meters. That's meters squared per second squared. So a joule is a kilogram meter squared per second squared. Okay. Okay. So let's keep going. Now, be careful here. Okay, so this only makes sense. This expression only works if the displacement and the direction are collinear. They're in the same direction. So this has to be a collinear work and force. Okay, we'll see how to deal with it if they're not collinear. The force that we have to consider is always the force in the direction of the placement, or the change in position of the placement. Right? So the force that's acting in the direction in which things is the work we're done. So for example, if I push down on a textbook, the textbook isn't moving. Right? So if the textbook is not moving, that means that in this case the textbook doesn't change position, right? So the delta D is equal to 0. So necessarily then the work has to also be equal to 0. No work is done when you're not changing its position. The work is only done if you actually are moving something. I can push on it as much as I want. I'm not actually doing work on it. I'm not changing its case gravitational potential energy. I'm not lifting it up or down. Not changing. I'm not pushing against some sort of friction or anything like that. I'm not doing anything against inertia. Right? The whole point is that textbook is sitting on that desk and it has inertia. It doesn't want to move. So if I push it, right, I'm doing work against that inertia, and that's the work that I'm doing. But if it's not moving, I'm not doing anything to change anything like that. Let's do an example here. So pretty straightforward example. We have a airport terminal employee pushing a line of carts at a constant velocity with a horizontal force of 95 newtons. How much work is done by pushing the cart 16 meters in the direction of the applied force? So it's always in the direction. We need to answer it in kilojoules. We'll see what that means. So let's write this down. So work is equal to force times the displacement. Right? That's the equation I just gave you. So it's equal to, what's the force? That's 95 newtons multiplied by 16 meters, which is 1,520 joules, or 1.5 kilojoules. 1 kilojoule, right, is 1,000 joules. So then, using significant digits, 2 sig digs, right? 2 sig digs. So our answer has to be in 2 sig digs as well. So our final work, 1.5 kilojoules. Okay, so that's how much work the guy is doing, right? So the guy, girl, whatever. The gender-neutral airport terminal employee is pushing a line of carts with 1.5 kilojoules to move them 16, right? That's how much work he is doing on the carts. We got to be careful. We got to think. One of the things I keep in mind, it'll become more significant later. Keep in mind that we're always thinking about what's the work being done on and what's the work being done by. So in this case, the airport terminal is doing work on the line of carts. Okay, he's doing the work. They are doing the work on the line of carts. All right. How about this? A force of friction on a sled is 120 newtons in the opposite direction of the sled's motion. Okay, so there's sled is sliding. You stop pushing it. The force of friction takes over and it stops in 2.4 meters. How much work is done by friction? So in this case, the work is done by friction to slow it down. Okay, so now we got to be a little bit careful. Okay, so the work is equal to, again, force delta D, right? But let's think about what this thing is doing. It's going from let's call this point position 1, D1, to position D, whoops, there it is. So it's going to a second point here. Let's call this D2. So it moved from here to here, right? Now the force, which direction is the force acting? The force is acting in the opposite direction to its motion, right? The force is pushing against the displacement. So in this case, we're going to have to say that the work is negative 120 newtons because it's opposing the displacement, right? My displacement is going to be this vector here, right, from D1 to D2, but the force is in the opposite direction. That's going to be 2 meters. So we end up with, what's 120 times 2.4? That's 288 negative joules. Okay, so that's how much work was done in stopping it. So in this case, we have a negative work, right? We've taken energy away from the sled. The sled is traveling with a certain kinetic energy, right? So we talk about, remember, kinetic energy. So that's the energy of motion. So the sled is moving, has a kinetic energy, and all of a sudden it's stopped. So therefore, we had to necessarily take this energy away. So in this case, this force of friction here is removing energy from the sled. The friction is removing energy. That's what this negative means here. So this is taking, in this case, we called it kinetic energy, right? And, oh, I can't spell. Pardon me. Taking kinetic energy away from the sled, right? So that's what that means when it's in the opposite direction, right? So we got to be careful. So what does that mean when there's a negative energy, right? In the first case, when it was the guy pushing the carts, he was giving the carts he was fighting friction, so it wasn't changing the velocity really, but he was imparting an energy onto the carts to move to change their position. Here, this friction is stopping the motion, so it's taking energy away from it. Okay. So again, this is the energy done by the friction in removing energy from the sled. Okay, the sled has lost energy now. Okay. So the question then becomes, what happens if we have the situation where things aren't in the direction, the force isn't the direction of the displacement? Let's say I have a block here, at this block, and I am moving it in the direction of delta D. Okay, and there's a force acting on it. So let's say delta D. Let's make this a vector here, and make that a vector there. Okay, the work now is going to be equal to the amount of work that's done in the direction of D. It's going to be equal to this piece, this vector here, right, which is the cosine of that force, right? So this guy here is actually equal to F cos theta, right? So it's the sort of the projection of it, the shadow. Imagine there's a bulb up here. There's a light bulb up here. The world's worst light bulb, no lamp. Okay, it's shining. Wow, the Mr. Stone's worst lamp of all time. But it's casting a shadow right here. Okay, this is the shadow that's being cast of that force, and it's F cos theta because it's adjacent. And it's going to be multiplied by delta D. So the work can end up, if we don't have it in the same direction, it'll still be F delta D, but it'll be multiplied by the cosine of the angle. And notice if the angle is 0, if they're collinear, cosine of 0, 0 equal to 1. And if they're at 90 degrees, if they're at right angles, the cosine of 90 is equal to 0. So if they're at right angles, if the thing is moving in this direction and I'm pulling up, let's say, and I'm not changing its position up and down, I'm not doing any work because none of the force is acting on it in the direction of the displacement. Because the difference, the angle there is 90 and the cosine of 90 is 0. All right. This has to do with something called a dot product that you'll learn maybe in grade 12 in calculus. Okay, but let's not worry about that. Okay, so you can think of it sort of as the projection. Let's try an example here. So a crate's being pulled by a rope at 26 degrees. It's dragged 18 meters. What's the work done? Okay. What's the force? Well, let's say the force is 120 meters. You hear noises in the background. That's my 4 children. Yes, I have 4 children. They are all at home, just like you guys. Things are crazy. So please ignore all the kids running around in the background. Thank you. I apologize. Hopefully they won't come barging in here and jump on me while I'm doing this. But let's say we have 120 newtons. I didn't put down the work, but whatever. All right, let's make it easy. Let's make it 100 newtons because I can. All right, so work is equal to F delta D cos theta. That's going to be 100 newtons. Oops, multiplied by 18 meters. Apparently they're doing jumping jacks in the downstairs. Anyways, cos 26. That's going to be equal to 1800 times cos 26. Calculator out. What are we going to get? 1800 times cos 26. So we get 1618 joules again. So 1.6 kilojoules. Okay. Apparently they're doing some sort of a workout downstairs. All right. So yes, that's the work done. So remember, it's just this cosine of my angle that allows us to get the piece that matters. Okay. So there's a bunch of word problems on the website. Okay. All right. So again, stay safe, stay home, do physics. All right. So best of luck. I'll post the answers as well on the website. The work is on our website on our Weebly. Remember, go to our Weebly. I'll post this video on the Weebly as well as our Discord. So best of luck and take care.